Boulat, welcome back. This is Boulat Bash from University of Arizona, who will speak about fundamental limits of entanglement-assisted covered communication over the bosonic channels. Welcome. The stage is yours.
Thank you, Yanis, first off, for organizing this workshop. It's been very interesting. Appreciate the invitation. I understand many of you are going to dinner soon, so I'll try to be brief. Of course, first, I must acknowledge the people who actually are making this possible, namely my graduate student, Michael Bula, who did most of the hard work on what I will present, as well as Christos Gagatsos, who is now an assistant research professor. The Optical Sciences College at the University of Arizona. And you just heard Saikat. He was also involved in the first paper that will be presented in this talk. And I have to acknowledge my sponsors as well, National Science Foundation of the United States, as well as the Office of Naval Research and Army Research Office here. So we have oh, this is interesting. I don't know why this happened this way. We have seen this, I think, throughout the session that the shared entanglement between receiver and transmitter can benefit tremendously the communication rate. And it was first, going back to the Bennett's famous paper, the BSST paper from 1999, in the bosonic channel case, which models very accurately pretty much any kind of a point-to-point channel that involves modulating electromagnetic radiation. You can have an infinite-fold improvement, at least theoretically, using two-mode-squeeze vacuum. And this is the Giovannetti as a result from 2003. Now, there is a problem with these two results. First, well, we have the benefit is limited to a factor of 2, unless there are two conditions are met. Noise power, noise being the channel noise right here, it's thermal in this case, has to be very large, and signal power is very small. And I don't know why the border was not disappeared previously. So this is the condition. This is the primary condition for this to work. And the what we want now is a regime, and I think that Saikat mentioned this in his talk as well. We want a regime which has low signal power and high noise to make the best use of an entangled resource. So how do you find this regime? Well, is it optical? Can we use this for optical comms? It's easy to achieve entanglement in optical domain, but relatively easy. But low signal power can be also had, but noise power is typically very low. So no. Radio frequencies, microwave radiation, kind of the stuff that cell phones use. We have really high noise power, Planck law driven, but also we can use high signal power, much more than 1 photon per mode. And thus it's not very useful. So as Saikat alluded at the end of his talk, there is a need for an application which puts you in a regime of needing to be transmitting at low signal power, yet in a high noise power. And that regime is not typical, but the one which I will discuss, which I agree with Saikat wholeheartedly, and not just because I've done most of my research, both in graduate school and here on it, but core communication is what this needs to be used for. Now, to describe core communication, first let me describe to you what it isn't, but what you're familiar with, because much of the security research that you've seen is dedicated to this. And this is a secret channel, Alice and Bob trying to communicate. They're trying to prevent Eve, the eavesdropper, from decoding the message. And there's crypto, information security, quantum key distribution, all sorts of solutions to this problem. Now, suppose we want to prevent the detection of the transmission in the first place. Many people care about this, including perhaps some of you who want to protect their privacy, of course, to organize a social unrest against oppressive government regimes, and needless to say, military is very interested in this kind of capability. So this is the setup for covert communication. Instead of Eve, we have Willie the Warden. All Warden does is attempt to detect transmission. He does not care about what you're transmitting. He just wants you to, he wants to know whether you're transmitting, and presumably he can punish you for doing so. Notice that secrecy does not actually solve this problem. You cannot use crypto and be purely crypto and be undetected. Quantum key distribution doesn't help either. What you need are two things. What you have to have is noise that is not controlled by the warden, by the adversary. Otherwise, if the warden controls the noise, there's a no-go theorem that I proved in 2015 that states that if there is no noise on the channel, quantum fluctuations, vacuum fluctuations are not sufficient for this. So you need noise. Second, you need advantage over the warden. In this case, what we're looking at is a shared resource of some kind, whether it's quantum or classical. This is the distinction I'm going to describe in this talk. So these are the ingredients that we need. And if there's anything you could take away from my talk today, it is that covert communication is fundamentally different from secrecy, because its capacity, its channel capacity or hello capacity is 0. Yet it is still very intellectually interesting because you can transmit a large number of bits covertly, the fact that the capacity being 0 notwithstanding. So how do you do it? Well, first let's discuss what makes communication covert. Two things: low average transmission power, that's the most important thing, and a signal modulation scheme, that's less important, and I'll describe why. We're going to consider a bosonic thermal noise channel that's described on the figure on the right. We're given n modes, and we have n as just time bandwidth product, for instance, and we assume that our adversary is fully quantum capable, except not having access to noise control or the share resource. Otherwise, he collects all the photons that are not received by Bob, and he has unlimited quantum memory, unlimited quantum computing capability, unlimited joint detection receiver. He has any quantum tool that an Eve in QKD has, but he just doesn't have control of the noise as well as access to share resource. So this is what we call quantum secure covertness. It turns out that, and this is in the paper that my student Michael Boulat has published in JSEC 2020, it turns out that the maximum number of photons per mode that you can transmit is given by this formula. We will not go into deriving it because it's long and complicated. But the takeaways here are that delta is a coverdness parameter. It's a constant. It's a constant that you set. And the smaller you set it, the less detectable you are. This C-cov is a channel-dependent constant. So you can see from the formula it only depends on noise and loss in the channel. It turns out, by looking at the square root of n in the bottom fraction here in the denominator, the photon number, average photon number per mode, has to decay with the number of modes that you're trying to use for transmission. So this is where the low average transmission power comes in. And it also turns out that the complex Gaussian or thermal modulation of coherent states or QPSK modulation of coherent states, which describe laser light, achieve this constant. BPSK and presumably other modulations take a constant penalty, but they do not take a scaling penalty. the scaling does not change as the constant changes for these modulations. So this goes to what I said previously about the signal modulation scheme being less important than low average transmission power. If you transmit using some weird modulation, you might stick out like a sore thumb to Willie, but it won't be as bad as if you were breaking the power barrier here. So that's another takeaway. So I want to mention that my earlier work happened to find the similar square root law for power. This is square root law. I should have mentioned this earlier. For power in classical systems, I started in additive white Gaussian noise channels, and then Matthew Block and Li Gongwan picked it up and proved this for the discrete noise channels. And that aside, the main question that we must answer is, what can we do with so little power? How much can we transmit? And this is the subject of the paper that we recently wrote and was published by the Journal on Selected Areas of Information Theory. The second paper on the list on the second slide of this talk. This was led by Christos Gagatsos and my student Michael Bullock. It turns out that you can actually characterize the number of bits that you can transmit, and so there is a notion of a square root law of covert-communications. This is a very this is what started in 2012 with my 2012 SIT paper, and here's its bosonic version. You have the number of bits m, and it turns out that you can transmit L, which is a channel-dependent constant, which we call the covert capacity, times square root of delta times square root of n, and plus some small terms. So our objective is to derive the constant L. The objective is to derive the covert capacity, and also to examine what happens when you use entanglement-assisted communication here. So, as I mentioned, SRL has been known since 2012, and I have to also give a shout out to Mehrdad Tahmasbi, who had characterized the total number of bits for classical discrete MMOS channels in his transactions on information theory paper in 2017. We used that for inspiration, and we also used the notion of capacity was inspired by Li Gongwan's 2015 paper. He has it there first. I have to give that acknowledgement as well. So this is the paper that I will describe. It turns out that we can actually derive the L for the non-entanglement-assisted capacity, and it just takes a little bit of math. What's more interesting is that entanglement-assisted assistance in the form of two mode squeeze vacuum state, which I denote as this figure, increases the scaling of covert communication bit throughput. So you can see this log of n times square root of n. That is much better than just square root of n. Not in relative terms. We're trying to squeeze everything out of the few photons that we are allowed to transmit covertly. And entanglement assistance gives us a opportunity to increase that amount of information by a significant factor. If your n is large, if it's say millions of modes, this is a large gain. So how do we get there? Let me. This is some pretty boring information theory. I'll try to cover it very fast. So what we need to do is we need to have, in order to communicate, Alice and Bob have to have correlations that are shared. and these correlations have to be unknown to Willy. So we're assuming everything is, I'm assuming that this code book Willy doesn't have it. And the way that it works is this position-based code, where you have m-bit message. There are 2 to the m of them. Each one of them is mapped to n states. So the total number of states you need is going to be n times 2 to the m. And it's very inefficient, but it works for the proofs, just like a lot of information theory. Alice's codebook and Bob's codebook are correlated. In fact, when you have coherent states, they're basically the same coherent states. You can just generate them at Alice and Bob's transceivers. For entanglement assistance, you generate 2 mode squeeze vacuum states. You send one of the systems to Alice, the other system to Bob. And this is how you obtain the codebook. Very simple. This is called position-based coding, and to my knowledge, it was first described by Mark Brody in his Quantum Information Processing article from 2017. So we ensure covariance by setting the bits of the photons per mode number per the prescription that was developed by Michael. This formula here. So that's easy. The capacity proof is more challenging, and this was the point of the journal on sectarians of information theory paper. So how do you prove capacity? How do you show the number of bits? First, the converse. You have to show that there is an upper limit to the number of bits you can transmit using this much power per mode. This is the idea of information theory converses. What you do there is you use the standard Fano's inequality as well as the capacity bounds, either the Holevo bound that was done, I don't recall when, I think in the 70s sometime, or the entanglement-assisted bound for the bosonic channels, which was Giovanetti's 2003 PRA. So that's relatively straightforward. What was not straightforward is the achievability. And that was because even though achievability is straightforward in finite dimensional case, which where you can use all sorts of methods going back to Holevo again, but Hayashi also has a nice book which several chapters are dedicated to all sorts of proofs of capacity. The problem is our Hilbert spaces that the bosonic channels operate in are infinite dimensional. So a lot of those results depend on dimensionality of the space being upper bounded, and thus don't work, at least don't work very easily. So what we did was we used the sequential decoding approach, which was described by Oscar, Mark Brody, and Mancini in the Proceedings of Royal Society A 2019 paper. And I'd like to thank Mark, by the way, for pointing these papers out to me. This second order capacity result was particular code worked. It gave us the achievability that matched the converse. And now I'll just present the formulas that we've derived, which is going to be quick. So first, I'll give the formal definition of the capacity of covert-communication, and notice that here we normalize by square root of n. In Shen-Holevo capacities, the normalization is n. So this is why it's called covert capacity, not standard capacity. The Holevo capacity for this channel would be 0. Limit as n goes to infinity of m divided by n is going to be 0 because m increases as square root of n. So it's not very informative quantity, but this is informative. And we can actually give the formula, we derive the formula for this, and there is the it's a multiplication of 2 parts. This is the C-cov from Michael Bullock's paper, and this is the co-generability that was in Christos Gagatsos' paper that we put in. Them together form the capacity. Now, the second order theorem that we use basically gives us this formula, this lower bound for achievability in the second order. And I will say that this is very similar to what one sees in classical channels. This is namely the Merda-Takhmaspi's work from 2017, has a very similar result to this, at least in similar form. Obviously, the constants are all different, which we had to derive. So the entanglement-assisted capacity, you can now see that there is a scaling factor change in the denominator, and but the converse is different. The constant itself is different, but the idea to derive it is the same. We again derive the formula for the lower bound and obtain the constants. And these formulas is what took most of the work on this paper. So let me conclude with the outlook. First, let me reiterate that entanglement shows a lot of benefit towards the increase in core capacity. The ongoing work, Saikat just described this as his receiver. I will note that we actually have derived the Shannon capacity of this receiver for the covert-communications, and it turns out that it is roughly half. The penalty is roughly half, as we expected from the entanglement capacity. So we are evolving this. Saikat also mentioned that we are looking at the potential impact of noise and loss in entanglement, code word, and distribution and storage. The preliminary results on this indicate that noise destroys the log of n factor. Loss alone simply changed the constant front. So, and this will be presented at ITW 2020, which was postponed from 2020 to April 2021, hence the weird designation. That's the work led by my student, Michael Boulat. And finally, a hard problem is how to characterize the amount of shared entanglement required to achieve this gain. The code book design that we currently have is incredibly inefficient. We want to figure out what is the minimum amount of shared entanglement that's needed. And that's a very complicated problem because, as Saikat mentioned, the quantum capacity of a bosonic channel is unknown, and it probably has to be used in here. So that's it. I don't think I ran too much over, but this is there we go.
Thank you very much. What do you think? Is this our first use case for entanglement assisted communication?
I would say this is the first use case that's actually useful.
Very good. And what do you need? What is missing? Why is it not on the road?
Well, first of all, if we need to build something like this, that plus we need to be able to distribute the entanglement to two parties and store it. This receiver, Saikat's receiver, as he mentioned, assumes that there is no loss or noise in the either modes of the two-mode vacuum. So in real world, we won't have that. Never. So we need to figure out a way to either distill the entanglement out somehow, or figure out a way to kind of bring forward the protocols that will enable the use of little entanglement. I think that my personal opinion is that I don't think we'll ever get a log of n factor. But what's going to happen with entanglement assistance is it's just going to increase the constant front tremendously. So and the constant will be dependent on the noise and loss. of the entanglement itself. And this is what my student Michael has found just for TMSV states. There is another thing he found that we are not going to present him at the ITW because it's more of a numerical proof, not an actual proof, numerical result, an actual proof. And that is, so TMSV, tomoscus vacuum, is optimal for entanglement-assisted communication in general. That's Giovanetti's 2003 paper that I mentioned previously. But when you have loss in the idler, in the idler mode, loss and noise, it actually seems that tomoscus vacuum is not the optimal Gaussian state for that. And we have interesting calculations that Michael has been doing. They're very hard. It's just a huge pain to carry them out. But it seems that just symmetry kind of breaks down in that case.
Okay, thank you.